Good morning, everyone. Yeah, this is now, we switched to Paris, to Europe, about the inversions of CO2 emissions. We've been heard it several times already. Urban environments comprise just 2% of the global land mass, but they are responsible for large amounts of CO2, of energy use-related CO2 emissions, according to the IEA, about 70%. And there's this political need to improve city emissions. And to address this, several dedicated in situ measurement networks have been set up. We have seen the results from Indianapolis, also Los Angeles, and here I'm going to talk about Paris. And during the CO2 Mega Paris project, 3 stations have been deployed, and they are complemented by 2 ICOS France stations. You see those 5 stations here, actually. And they are located roughly in the southwest-northeast direction, so that's along the main wind directions of Paris. And then following, I present you the inversion results using an analytical Bayesian inversion tool to estimate the Ile-de-France or Paris area CO2 fluxes. And since we're quite limited in the number of stations, the idea is to use the concentration gradients, the CO2 concentration gradients between downwind and upwind stations to adjust an inventory, the Airparif inventory, but to keep the spatial distribution of the inventory. So here, you see schematically the inversion framework. So we start with prior emissions from Airparif 2008 for fossil fuel CO2 emissions in Ile-de-France. And for the remaining parts, we use the ETCA inventory. And for the prior NEE fluxes, we use ECMWF C-TESL products. In order to build the mapping from to map the fluxes into the observation space, we use Schmidt and Airparif and C-TESL to build the observation operator. Schmidt is forced by ECMWF wind fields. And in Ile-de-France, it has a resolution, Schmidt, the atmospheric transport model Schmidt has a resolution of 2 kilometers. And boundary conditions are derived from the coarse grid inversion provided by LMDZ. Regarding the observation vector, so we assemble the concentration gradients between an upwind and downwind station during the afternoon if wind speed is greater than 3 meters per second. The main idea of this gradient selection is to remove the upwind signal from both the measured and the observed the measured and the model CO2 concentrations. And it assumes that between upwind and downwind sides, the emissions are concentrated between the upwind and the downwind sides. So to be more precise, so if the wind is from the southwest, we take Gif's reference and take assimilate Mauger minus Gif and Gonesse minus Gif into the system. While if the wind is from the other direction, it's the other way around. So it's Gif minus Mauger and Gif minus Gonesse that is assembled into the observation vector. And with this incredience, we correct the 6-hour mean fossil CO2 fluxes and the 30-day mean NEE fluxes for each 6-hour window. But we keep the spatial distribution of them, so we only rescale Airparif and the C-TESL flux maps. Regarding the uncertainty, so we use a 20% uncertainty for the fossil fuel CO2 prior emissions and allow some weak correlation, while the observation error matrix is, we don't assign any correlation, and we use a 3 p.m. Uncertainty. So we do this inversion for every month separately, and what you see here is a comparison between of hourly and modeled and measured gradients. Prior and after the inversion, you see a much better agreement between the gradients. One drawback of the gradient selection is actually that you significantly lose lots of data. For example, here in February, you have just in the first 2 weeks data that constrain the budgets, while here in June you have just 4 days where you constrain your monthly budgets. So I come now to the first results. So these are the monthly CO2 emission estimates. In blue, you see the Airparif 2008 estimate. It has actually a very weak seasonal cycle, as Airparif only, well, this inventory is only compiled for 5 months, so 1 month, 1 August, 1 month in fall, 1 month in winter, 1 month in spring, and then for July again. And in red, you see the posterior fluxes, so after the inversion has done its job. And you generally see an amplification of the seasonal cycle, a strong amplification, and that also gets a nice, reasonable correlation with temperature. For example, highest emissions in December correspond exactly to the month with the lowest temperature. This makes perfectly sense given that that home and commercial heating contribute lots to CO2 emissions during winter. You see here there's the estimate for the annual budget, and the posterior, the inversion gives an annual budget that comes very close to the newest Airparif 2010 inventory, 41 megatons CO2 compared to 42 megatons of CO2. So I now come to more sensitivity tests. So these are the monthly estimates from different subsets. So I selected the subsets according to the wind direction as well as to the individual sites. And you see on the greenish lines, this is actually when we use the gradients to Gif, which means when the winds are from the southwest. And you see that this reveals this nice seasonal cycle with highest emissions in December and lowest emissions in the French summer month. If you take the winds from the northwest, if you assimilate only data when the wind is from the northeast, we see that the fluxes don't differ too much from the southwest gradients, but the seasonal cycle is less apparent. Particularly here in December, you have lower emissions than in the other directions. August is special because we have only data from the southwest wind, so this is basically the northeast gradient give back the prior because we have no data to constrain the budgets. So what could cause actually these differences, for example, in December? Just a few thoughts. So we actually have, we can't control, with the current inversion setup, we can't control fluxes, fossil fuel fluxes from outside Ile-de-France because we have no network to do so. And a second point, if the winds are from the northeast, you have that might be that the CO2 fields from northeastern France, from Benelux countries, from Germany, so from countries that emit a lot of CO2 emissions, that these CO2 emissions may be not well represented in our model. While if you assimilate data from the southwest, this is actually CO2 fields from a very rural area, which might be better represented in Schmidt. And another point is we use this 3-meter minimum wind speed criteria in order to minimize the impact of local sources. But between Gonesse and Montgé, there's the Charles de Gaulle airport, which is the second largest European airport after London Heathrow. And it might be that these local sources also affect our results. So flat prior experiment. So the idea of this flat prior experiment is to check if the total monthly emissions, how much our results are sensitive at them. And the idea is to keep the monthly emissions flat, but retain the observation operator. So the only thing is just to modify the setup that the monthly emissions are flat. So I use 3 different flat priors. One's the annual mean at 4.3 megatons CO2 per month, one at 5 megatons CO2, and one at 3. And color-coded, you see the posterior fluxes. And in red, you see also the results from the default setup. And what you generally see that the monthly posterior fluxes nicely converge to one value. For example, December, even when you start with 3 megatons CO2, you come up to values that are very close to each other. So the conclusion of our flat prior experiment is really that the seasonality is driven by the observation, so that the observation are responsible from the temporal variations of the monthly budgets. So another point is how sensitive is our system to the observation operator. So for that reason, I used an RER France product that has actually the same special resolution as the Airparif data. And you see nicely that, for example, so in red is again Airparif, while in green is the one where we used the RER, and they are scaled back, but they are again scaled to the same product. And you see, what you see is in spring you have very nice similar results. You see also they agree very well in fall. Sorry, in fall they agree very well, the greenish and the reddish line, while in spring they also agree very nice, also in summer. But in winter there seems to be a strong difference, so that means that the monthly budgets are actually quite sensitive on the special distribution of the flux maps, which is quite interesting. Okay, I'm already going to my conclusion slide. So We have just 1 year of CO2 megaparis data, but the results, and we have only 3 stations that we really employ, but the results are quite promising. We get a nice, reasonable emission temperature correlation. We have the highest fluxes in December, which are nicely correlating to the lowest temperature. We have annual budgets that come very close to the newest Airparif inventor, which is also very nice. With the flat prior experiments, I showed that the observations are mainly responsible for the seasonality of the monthly budgets, which means that really they are responsible for this difference between the different months. And also showed you that the monthly budgets converge also from the different subsets. So when I selected according to the wind directions, I selected according to different wind directions and the different gradients. You see also a convergence of these gradients, but there are some remaining discrepancies, particularly in December, which might be attributed to local or remote fluxes that we are not properly controlling in our inversion system. Gradient selection, so assimilating concentration gradients between upwind and downwind sides and to control the budgets which are concentrated between the two sets is a very simple approach, but a kind of critical step forward estimating city emission, particularly at least for our case in Paris with a nice terrain. It's not very complex, so it seems to be working nicely, but it doesn't mean that it's working for cities with a much more complex terrain. And one drawback of the gradient approach is actually that the data selection is quite strict, so you really lose a lot of data, and there might be some filtering needed to use more information out of these data. Okay, thank you.
Thank you, Johannes. We have time for a question or two, so we'll start with Kevin.
Yeah, it's in this observation error matrix, which accounts also for representative error, model error, and aggregation error, as well as for the instrumentation error. And to design this observation error matrix is always quite critical, but there's a method called from Gérald Desrosiers, which you mathematically ensure that you don't do anything wrong, actually. So you ensure that the setup of the matrix fulfills the mathematical properties that are needed in the inversion setup.
Ken.
There must be biological fluxes in the summer. How can you solve for the emissions from Paris without taking into account biology at the same time?
Question was for biological fluxes. How do we resolve those?
Well, how is it taken into account in this work? You said that.
Well,
Got it. Okay.
can I go back? Well, it's C-Tesla accounts for biogenic fluxes for the whole. I just showed you here. I just showed you the net CO2 fluxes, but the biogenic fluxes are taken into account in the inversion system.